The double pendulum is a well-known example of a chaotic system. You can find many online and many YouTube videos demonstrating such a system. However, I can't seem to find many 3D double pendulums for whatever reason. When I decided to make this my next project, I very quickly discovered why. To begin, I needed to find the equations of motion for this system. I wrote a quick paper that I will link in the description that gives full equations of motion derived using Lagrangian mechanics. As you can see, they are huge, taking up the entire page. Initially, I wanted to do the equations by hand, but after taking roughly 2 hours and a full sheet of printer paper to derive just the Lagrangian of the system, I gave up and looked for an alternative. Then I found SymPy, a Python library that algebraically calculates expressions for you and can be converted to any programming language you want, including LaTeX, which is what I did for the paper instead of writing everything out by hand. The equations of motion can be seen in the JavaScript source, which once again are massive. In order to simulate any system in physics, you need to find the value of the second order variables. But because the equations of motion are so complicated, finding an analytical solution isn't really possible. Luckily, the second order terms are all linear, meaning you can treat all 4 of these equations as a system of linear equations that can be solved using linear algebra. When I did this and fixed the azimuthal angles, the system worked like a 2D pendulum, but if the azimuthal angles differed even slightly, the system quickly blew up to infinity. In order to fix this issue, I found 3 things you need to do. 1, you need to do 200 time steps per frame. 2, instead of using Euler's step, you have to use the 4th order Runge-Kutta method. And 3, you have to use Tikhonov's re-regularization method. This turns out to be a common problem in computational physics. If you have an ill-conditioned matrix, which is a matrix for which the determinant gets very close to 0, a computer will very quickly accumulate round-off errors for each iteration. Tikhonov's method basically stops the matrix from getting too close to singularity by adding a small lambda parameter to the diagonals. After all this was implemented, the 3D pendulum was solved.